Hi, my name is Sungho. I'm a PhD student working on the development of the zero-power IR photo switch that's designed to detect human presence without relying on the conventional electronics, which typically have lots of limitations in terms of power consumption, their device size, and the sensor cost. In today's demo, I will first go through some background with a few slides to talk about the motivation of our project, the background of our technology, and how far we've achieved with the technology compared to the commercial off-the-shelf sensor counterpart. And finally, I'll briefly talk about what we want to do moving forward with the technology as well. And then we'll show you a couple of experimental demonstrations of human body detection using our core technology and how they could outperform the commercial sensors. We started this project with the idea to develop a very small, low-cost, and easily deployable IR sensor that can continuously monitor the thermal radiation from a human body without consuming any electrical power in standby. This technology can be very useful to monitor any unwanted activities, such as border crossing or smuggling, without having to rely on the gigantic sensor systems or reliable electrical power grids. In particular, we are targeting specific applications in the indoor or semi-covered environments such as bunkers, caves, or tunnels, where there necessarily isn't any reliable power source such as electricity or sunlight. Which means they cannot really afford any state-of-the-art human detection systems such as the integrated fixed towers or the radar units that are currently in place along the borders. So the core technology in this project is a micromechanical photo switch that can harvest the electromagnetic energy from specific IR radiations in order to implement on and off switching without relying on any electrical power, including active electronics or sensing elements. And this is groundbreaking because when it comes to hundreds and thousands of sensors being deployed in the field, it is quite impractical to maintain that many sensors periodically. So our goal here is to implement this novel switching technology in between a power source such as a battery and some active electronics such as wireless transmitters, and use our smart switching to power these active electronics only when it's needed. So in this project in particular, we have developed the capability to design this micromechanical photo switch so that it is only sensitive to the thermal radiation from a human body. And here is a brief comparison of our zero-power IR human detector and the passive IR or PIR sensor, which is a fairly well-known and widely adopted commercially available IR motion sensor. Of course, unlike the PIR sensor, which needs to be constantly on to continuously monitor the human body, we can extend the typical battery lifetime of human sensors that usually lasts about a year to more than 10 years using our zero-power sensing technology. And we can achieve all of this in hundreds of microns in size, which is orders of magnitude smaller than the PIR sensors, and the capability to batch fabricate our sensors drastically reduce the sensor manufacturing cost as well. And finally, because the PIR sensors inherently rely on the motions of a human body, there are a number of scenarios where the sensor gets falsely triggered, which can be completely solved by our technology that can actually detect the presence of a human body rather than the motion. Now, there are a number of potential applications that can benefit from adopting our technology, but in this slide, I'll give you two examples where we think our device can make a huge impact. The first example here is the coastline safety, where you want to alert the field officers when there's any suspicious activities, usually by a group of people walking a very narrow and undeveloped pathway, and typically at night, which means you can't really access a reliable power source. And we can use an array of our devices to detect such an activity and even distinguish those groups of people from the harmless target sources such as individual hikers. And we'll show you later how we envision this particular application in one of the demo videos. The second example here is the home automation, which is already increasing rapidly in its market size, but we found out that there still are a lot of room for their devices to improve, including their battery lifetime, the manufacturing cost, and their accuracy, and we believe that our technology can really make those devices more reliable and marketable with a more competitive price. By leveraging such distinct and unique features of our device, our group is currently seeking to expand this technology into a commercial market. We really think that this technology can be exploited in a number of applications, and to really explore this, we have recently incorporated a startup company called Zapster Technologies. Right now, the company is looking for transition partners and seed fundings for us to develop the sensor system, to mass manufacture our sensors, and also to study the market opportunities in the variety of applications, including but not just limited to the homeland security and private applications. What we have here is a setup where we use our micromechanical photo switch to trigger these lights only when there's a person nearby. In other words, the system is going to remain completely dormant without consuming any power when there's no one in the room. We have our device currently in this vacuum chamber in order to minimize the thermal loss if it was otherwise in the atmospheric pressure. And as you can see, our device is facing upwards in order to detect a human walking or present in the horizontal direction. We need to redirect the IR power from the person nearby to the device chip by placing this mirror in the device's field of view. Then our device is connected to a load switch which controls the power of the lights. In this demo, we will first show triggering of the lights by changing the environment from no one in the room to when there's someone present in the room, which is going to activate our zero power IR switch, hence the lights.
So here you see a Zepsor chip that contains about 100 of zero power human detectors, and as you can see, the chip is hosted in this package. And here now you can see how we do an industrial standard vacuum packaging for the chip with an infrared transparent window. So this is how the fully packaged Zepsor device looks like as of today. So here you see a complete development board where we have the vacuum packaged Zepsor chip that is now connected to a board that contains a battery unit as well as a radio transmitter that communicates with a central hub upon a detection of an event of interest. So we are now working on miniaturization and system integration. And as you can see, all the components that are shown here for our development board will eventually fit in a device that has this sort of form factor. So it's the size of pretty much of a golf ball, and it fits in the palm of a hand.
In the following demo, we're going to show you how the sensor network works based on our zero-power human body detectors. We're going to use the motion control light to mimic the activation and wireless signal transmission of our device. The receiver will process the data from the sensor node and make decisions based on the sequence they've been activated and how many of them being activated.